So we've got our data. We've just got our four columns that we've plotted here, and we can see the underlying sort of structure of the data. But we want to imagine that it's actually much higher. But I didn't want to use real high dimensional data because then you couldn't actually view it at all, and you just have to trust that the PCA was kind of working. So let's run our PCA. So we're going to make a variable called PCA that's going to store the output of the per comp, and we're going to put in our D data frame, and we're always going to say scale equals true. The only time we're not going to do that is we just want to play around, right? And we need to scale our data because it's looking for the axis of maximal variation. And you can see that this body mass goes from 3,000 to 6,000. It's got a 3,000 range, while some of these other ones only have a range of 6 millimeters in the build depth. So the PCA, if it doesn't scale the data, is going to think this is very important, right? There's huge amounts of variation on this axis, but it's not real. Like, it's not really more variable in this axis. It's just it uses bigger units. So when we scale the data, it divides each axis by the standard deviation. It also subtracts off the mean, right? So the data is z-scored. We subtract off the mean, we divide by the standard deviation, and it makes everything in units of standard deviation. And this is a very common thing that happens in data analysis. It's called normalization or z-scoring, and it gets rid of that idea that one axis, one variable, one feature is more important just because it's got bigger numbers. We don't want the algorithm to think that. So we press enter, and it runs almost instantly because it's a very quick little algorithm. And so we've done our PCA. Okay, now PCA objects have a bunch of stuff inside them. If you're in RStudio, we can actually just find it. We can click on it, and we see what's inside it. We have this SDEV, the standard deviation of each axis. We have the rotation matrix. We're going to be talking about that in a little bit. Center, which is the mean of each axis. The scale, actually, the scale is the standard deviation. I don't know what the SDEV is right now off the top of my head. And then X is our data projected on to the principal components. All right. And let's first, right, let's sort of jump straight to the good bit. Let's just see. So if I go the head of PCA dollar lowercase x, there we see it, right? So here's our data on principal component 1, that axis of maximal variation. Here it is on principal component 2. And so now we should be able to say plot, and we want PCA dollar x, and we can use those square brackets again to say we want every single row and the first column on our x-axis. I'm just going to copy and paste that, and every single we want, so we $x to select that x data. We open our square brackets. We say we want every single row, so we don't put anything in the row, and then we want the first column. And then we do the same for the data we want to put on our graph. On the y-axis is going to be PCA $x. We want every single row, but the second column, i.e. this is PCA1 and PCA2. And we press enter, and we get this. All right. Let's do our trick we did before, where we say the color is given by as factor the data frame dollar species. All right. And there we get our representation of our data. Now, the first time, or probably the second time, or the third time you do a PCA, it's very hard to kind of feel what this means, right? But I want to go through it again. We've just grabbed our ellipsoid of our data and we've just twisted it around however was best so that that axis of maximal variation now sits here on this x-axis. And this axis of second biggest variation sits on there. So we just grabbed our data, we twisted it around through that 4D space. I'll give you a shiny dollar if you can imagine what that must look like. And put it on the graph, and we get our green one as before is sitting way off, but actually the red and the black are largely separated, so we can pretty much be certain we have 3 different populations. I mean, we know we do, right? Because it's species of penguins, but maybe we didn't know, it wasn't something like that, and so it can be hard to be certain. And now what we can do is we can do a summary on our PCA object, and it tells us how much variance is explained, this cumulative proportion. Or it says, well, we'll go through both of them, right? So it's saying, if you look at just PC1, you can explain 68% of the variation. If you look at PC1 and PC2, you explain 88% of the variation. And if you could look at PC1, PC2, and PC3, you've basically explained all of it. 97% of the variation, the variance of the data is explained by these 3. But to be able to get to nearly 90% through 2 principal components, this tells us a collection of things. It tells us there's huge collinearity in our data, i.e. there's lots of these dimensions that are unnecessary. Right? And you can see that because PC4 only explains 2% of the variance of the data. So basically there's no information in PC4. PC3 only explains 10% by itself, or 0.9%. PC2 explains 19.5%, and PC1 explains 68.6%, right? So basically these first 2 components explain heaps of the variance. And this also says that our data is like an ellipsoid, it is like a sausage, and basically it's almost like a flat sausage, right? That we don't even need to imagine our data as it being a 3-dimensional sausage. It's really just like a flat disc. What shape is that? I don't know. I can't think of anything that takes on that shape. A deflated rugby ball. That's what our data kind of looks like, which was not immediately apparent from looking at the pairs of the data. Okay, but how did PCA do this, right? And what is sort of the secret sauce, right? The secret sauce of the PCA is this rotation matrix, or these loadings as they're called, right? So PCA dollar rotation, we print them out, and it says, if we want to project our data onto principal component 1, we take 45% of the bill length, we take minus 40% of the bill depth, we take 57% of the flipper length, and we take 54% of the body mass, right? So this is our principal component, and because basically all of these numbers are very close to 0.5 or minus 0.5, this is basically saying if we can imagine a 4-dimensional scatter plot, or let's just stop trying to imagine 4-dimensional. If we have a 3-dimensional scatter plot, our axis of principal variation just goes on that diagonal between all 3. Now it's actually going in the negative direction of bill depth, but it's the same thing. Everybody is sort of growing all at the same time. And we can kind of prove that this is how it works, okay? This rotation matrix. And it's a little bit of a pain, it's not too bad, right? Now we've talked about the fact that the principal component the PCA, before it does the maths, it scales, it normalizes the data. So that's what we have to do. So what we're going to do is we're going to just take a copy of our data frame, right? We're going to go D2 equals D. So we're just taking a copy of D. Okay, and then we have to go, and this is going to be a little tedious, and there is a faster way to do it, but I don't want to introduce any new sort of syntax or function they have to. So we're going to go D2 dollar, let's work with bill length first. All right, so we want to normalize it. How are we going to do that? Well, we're going to get our data. We're going to subtract off the mean of the data, right? And then we're going to divide it by the standard deviation of the data, SD of the data, right? And that is how the PCA do, right? That is its first step. I'm just trying to make sure I got all the brackets in the right place. I think I do, right? Enter. Okay, and then we're going to work through the other one. So if we go D2 dollar bill depth, right, that is now going to be that value minus its mean divided by its standard deviation. We're going to go D2 dollar flipper length and this is going to be normalized to D2 dollar. Oh, hang on. Flipper length minus the mean of the flipper length, all divided by the standard deviation of the flipper length. And the final one is D2 dollar body mass. And we're going to say that is equal to the body mass minus the mean of the body mass, all of that divided by the standard deviation of the body mass. All right, now, if that has worked, now if we run pairs of D2, everything should be normalized. And so we see it looks right. So on every single axis, the mean sits at about 0, and the whole thing takes up about 2 standard deviations. All right, and that's what normalized data should look like. Okay, and now everybody shares the same unit. It's just in standard deviations. How many standard deviations from the mean is each data point? And so we can look at our data. We go here to D2, and there we see it. All right. Now, what we're going to show, well, what our goal here is to kind of do the PCA projection manually, but it's not going to be that hard. All right. So we're going to go PCA dollar rotation, and let's see how it works. Right. So if we want to project our data onto PC1, we get that loading, the bill length loading times the bill length. Okay. So we're saying I want 45% of the bill length. Then I add on minus 39% of the bill depth. Then I add on 57% of the flipper length. And then I add on 55% of the body mass. All right, let me just double check. So 45, 39%, 57%, and 54.9, and the values are minus 89, 77, minus 1.42, and yep, and I press enter. Okay, minus 8.9. So that first penguin, when projected onto the principal component 1, should have a value of minus 8.9. And we should be able to see that because if we go to our PCA $X and we want the first row, which is the first subject, there it is projected onto PCA1. PCA1 gives us minus 1.05, and that's what we calculated manually by looking at these loadings. Oh, so I know that was a little bit of something different. All right, so let's just go through it again. Right, so principal component analysis. What it does is it figures out where our axes of maximal variation are. It projects our data onto those axes of maximal variation, and those axes are described by these numbers we see in this rotation matrix, or the loadings, right? But another way to think of these loadings is they are to say, in order to project things onto principal component 1, that is that line that is the axis of maximal variation, we take 45% of the bill length, we take 39% of the bill depth, we take 57% of the flipper length, and 54% of the body mass. And when we calculate those, we get the data projected onto PC1. But that's exactly the same idea as both that graphical interpretation of we've put a line through our data and then we've projected our data onto it. And that's exactly the same idea as just grabbing the whole cloud of data, the sausage of our data, and just cranking it around so that it's its long axis is sitting on the x-axis, its next to longest axis, its widest axis is on the y, its next to longest axis is on the z, and I don't know what the letter is for the fourth dimension, right? Um, and we can, of course, interpret these loadings to a certain extent. So if we look, well, let's just print it out again, just for, uh, so as I saw, PC1 is basically an equal mix of all of the underlying um, features, meaning that our axis of longest variation is basically a collinear line that goes up the middle between all of our variances. But our second principal component has something different. It basically does not contain any flipper length or body mass. So this information is not particularly useful. There is not much variance explained in that. Now, if this is true, and honestly, I haven't looked at this, so let's hope it is true, that when we plot these two against each other, we should get something more like a circle. So let's see if this is true. Flipper length, I'm worried it's not. Sorry, not like a circle, the opposite of a circle. Flipper length versus body mass. Yeah, so this is just, when we compare these two, and if we were to plot a line through these two, there's very little data off that line, right? While if we look at principal component 2, which is build length versus build depth, we get something much more like a circle. So if we plot a line through that, it doesn't explain much of the variance, which is to say we need this information. We can't just discount it because there's a lot of stuff going on in this area. So it's very important to keep these kind of values, but we can kind of throw out these kind of values, or at the very least reduce them to a single dimension, because that's the key. That PCA by itself isn't really a dimensionality reduction algorithm. It's a data rotation algorithm. But the point is that after we've rotated the data, we can ignore PC3 and PC4. And let me show you why I say that. If we do pairs on the PCA $X, here we see what the data looks like. So here is PC1 versus PC2, and we get, nice interesting separation of our data. But if we compare PC3 to PC4, then you just get circles, right? So there's nothing going on. There's no information here. This just looks like a normal distribution. But as we go up and we look at PC1 versus PC2, or even PC1 versus PC3, we get interesting stuff going on. But these lower ones don't really have anything useful, so we can just ignore them. They don't add any information to the data. We can just still look at PC1, PC2, and if we really, PC3 would probably be pretty handy, but plotting three-dimensional data is you know, pretty tricky. So that's PCA, this way of rotating our data so that the first and second axes, that is PC1 and PC2, which are the same things as the direction of maximal variation and second most variation, they are kept. So it doesn't inherently reduce the data, but it makes it easy to ignore the higher principal components, especially if when we look at the summary of our PCA analysis, and we see that most of the variance is explained by these first two dimensions. In this case, it would be perfect if we could keep PC3, but PC1 and 2 do a great job of explaining the data.